Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous lecture, you learnt about Single-Layer Perceptron, a hands-on session in which you have learnt how to implement a single-layer perceptron model in Google Colab. Together with that, you have got familiarized with the basics of the Google Colab environment. In today's session, let's discuss about multi-layer perceptrons, which is the foundation of deep learning models and artificial neural network. So, I'll go to the contents for today's discussion session. The contents go like this: introduction to multi-layer perceptron, comparison between single layer and multi-layer perceptron, feed-forward neural network, and then we touch upon shallow versus deep neural networks. So, we'll start with what is a multi-layer perceptron. So, multi-layer perceptron is a supervised feed-forward neural network which is composed of multiple layers, and these layers include an input layer, a hidden layer, and an output layer. And each of these layers consists of a set of perceptrons which are called as neurons. So, if we see this picture, we have an input layer here, we have a hidden layer here, and an output layer here. The input layer consists of the neurons, and the inputs come to these neurons, x1, x2, x3, x4, these are the inputs to these neurons in the input layer. Then we will see that there are similar neurons in the hidden layer as well, and all the neurons are interconnected. That means there is a connection between the first neuron in the input layer to all the neurons in the hidden layer. If you can see, all are connected, and similarly for second neuron, third neuron, and fourth neuron in the input layer. And then these hidden layer neurons are all connected to the output layer, and from the output layer we get the output of the model. Now, in your last session, you all have learnt about single layer perceptron, and today we are going to learn about multi-layer perceptron. The first very basic multi-layer perceptron you have seen in my previous slide. Now we will have a comparison between a single layer perceptron and a multi-layer perceptron. So, if you see, this is a single layer perceptron where these are input neurons and these are the output neurons, and the connections between the input and the output neurons, they are having some weights which are nothing but the importance that you give to each and every input neuron. So, in case of single layer perceptron, which is this image, there is no hidden layer. The input neurons are directly connected to the output neurons. Whereas, in multi-layer perceptrons, the input layers are connected to the neurons in the hidden layers, and they are connected to output neurons. Okay? So, what happens is there is a hidden layer of neurons between the input and the output. And here also these connections or the edges are having some weights, and these weights decide how much importance to be given to each of these neurons, to the input neurons. Of course, from the hidden layers to the output neurons, when they are connected, there also we have the weights which decides how much importance will be given to the input that is coming from this hidden neuron to the output neuron. Now, in the second figure, you see there is only one single layer of hidden neurons. That means one single hidden layer is there. Multi-layer perceptrons can have only one hidden layer, or it can have multiple hidden layers. So, my third picture is having multiple hidden layers, and it is also an example of a multi-layer perceptron model. So, In single layer perceptron, we don't have any hidden layer. Multi-layer perceptrons can have one hidden layer or multiple hidden layers. Now the next question comes, why do we need multi-layer perceptron? What is the requirement? Multi-layer perceptrons are used because they can handle complex data sets which are not linearly separable. Now when we tell about complex data sets which are not linearly separable, what are those data sets? Where exactly we want to use these multi-layer perceptrons? They can be used in image recognition, like handwritten digit recognition, where your input is an image. It can be used in natural language processing, like sentiment analysis. These data are not linearly separable data. They are much more complex data. And it can also be used in speech recognition, like voice to text transcription and similar applications like that. And these multi-layer perceptrons, they have the ability to learn complex patterns from a very large volume of data, which is an essential tool in machine learning. Okay. So when the data set is large, and which is the case in lot of our real world problems, we require these multi-layer perceptrons because they can handle large volume of data. Also, they can handle complex data sets like image, text, speech, etc. And they can solve a lot of complex problems. Now, we will quickly have a glance into the working of a perceptron. This you have done in your previous sessions in single layer perceptrons also, but I will just glance it through once more. So we have these input features x1, x2 to xn, and the perceptron, it receives n features as input, x1, x2 to xn, and these features are connected with some weights, which once again I repeat that these weights decide how much of importance we give to each and every input. And once they come and get connected here in this neuron, there are two activities that are done there. One is the summation, which is basically the multiplication of the weight with the input. It's a linear combination of all the weights into input, and then the output will pass through some mathematical function which we call as the activation function, and then that result from the activation function goes as the output. We will have much more clarity of how these calculations happen in multi-layer perceptron when we go to the next slide. Now, one thing I would like to highlight here is, if you want a perceptron to be working, the input features must be numeric. That means some numbers. If we have some non-numeric input features, they need to be converted to numeric ones in order to use a perceptron. So these are the requirements for working of a perceptron model. Okay. Then we go and see what is a feed-forward neural network, and this feed-forward neural network is basically the way a multi-layer perceptron works. So we will see we have an input layer that we know, and in this input layer we have two input neurons x1 and x2. Then we have two neurons in the hidden layer. Now we will see how these connections, how these weights and other things are given in a multi-layer perceptron model. You see, the weight associated with the x1 input neuron is W11, and weight associated with the neuron x2, the input neuron x2, is W21. Just keep an eye on the nomenclature, how we are naming these weights. It is from where it is going to whichever neuron it is going. So W11 refers to the weight. This is the nomenclature we will be using in our lecture. W11 means it is going from X1 to the first neuron in the hidden layer. W21 means it is going from X2 to the first neuron in the hidden layer. Similarly, X1 is connected to the second neuron in the hidden layer and the associated weight is W12, and when X2 is connected to the hidden layer neuron, here it is the weight associated is W22. Then there is a term which is the bias term, which goes to both the neurons of the hidden layer. Now, what happens after these connections are done? Inside the hidden layer, as I told in the last slide, there are two mathematical operations that happens. One is the summation and another one is the activation function. We will see exactly what happens in those two steps. So, the first part, it is a weighted sum of the inputs. What do I mean by the weighted sum of the inputs? It means the first part takes the weight W11, multiplies with the input neurons value X1 plus W21, which is the weight associated with X2 when it is connected to the first neuron in the hidden layer, W21 into X2 plus the bias term B1. Similarly, for the second neuron in the hidden layer, the weighted sum of inputs is Z2 equal to W12, which is what is W12 here. This is W12 is the weight associated with X1 input when it is going to your second neuron in the hidden layer. So, W12 into X1 plus W22 into X2 plus B1. So, this is called as the weighted sum of the inputs because the inputs we are multiplying with the weights to give a certain amount of importance to the input neurons, okay, and the biases we are adding. So, this is the first part of the calculation. Then what happens after this? After this, there is an activation function. We have not discussed activation function till now. It will come in my next session, but for time being we will understand that activation function is a mathematical function which takes this weighted sum of the input, passes through the mathematical function to give an output which goes to the neuron in the next layer. So, here the activation function is G, which takes Z1, passes Z1 through the activation function. Later we will discuss what type of activation function, how they change and other things. Right now it is only a mathematical function operation, and then it gives the output A1. Similarly, in the neuron 2 of the hidden layer also, the activation function is G, which takes input Z2, which is my weighted sum of inputs, and then it gives the output A2. Now, this is the work that is happening inside the hidden layer. Then we have another neuron which is basically the output layer, and this neuron gets the input from neuron 1 of the hidden layer and neuron 2 of the hidden layer. Now, as I told, after the activation function is working on Z1, we get A1 as the output, and this A1 is now going to the output neuron, and once again we have the weighted sum of the inputs Z3 equal to W1K, which is the weight associated with this connection, into A1 plus W2K, the weight associated with the connection between the second neuron of the hidden layer and the output neuron, and we get the weighted sum of the inputs. In this case, there is no bias which is taken here. Now, the activation function, once again there is an activation function here which is which is G, and it passes Z3 and then gives me the output A3. So, the output of your output layer, this is basically your output layer, is nothing but A3. Now, suppose your target is y. What is the meaning of target? Target means the ground truth value, the actual value is y, and the predicted value from the neural network is A3. Then there is something called as a loss or the error, which is a function of y and A3. It means the loss or the error term is the difference between the predicted and the ground truth. Okay, it is the difference between these two. Now, that means the loss is a function of your ground truth value or the target value and the output that you are getting from the neural network. The entire process that I explained till now is called as the forward propagation, which means the information is passed in the forward direction. Now, what is the main aim of a neural network? The main aim is when we are predicting something, whatever it is, whether we are predicting a class of an image, or whether we are predicting the weather, or we are predicting anything, we want the prediction to be very, very close to the actual ground truth value. Now, for that one, what needs to be done is the loss or the error should be minimized. Now, how to reduce this error? Now, if we see, the loss is a function of the ground truth or the target value and the output from the model. Now, we will just quickly have a, till now I have explained all in terms of x1, x2, x3, x4. We will quickly have a look into a numerical example, and then we will go and see how the loss can be reduced in case of neural network. So, suppose we have inputs x1 and x2 as 1 and 2, bias b1 equal to 0.5, and the activation function used is the sigmoid activation function. Once again, it's a mathematical operation, and which is given like gx equal to 1 by 1 plus e to the power of minus x. So, that is the activation function that we use here, and it is called as sigmoid activation function. Right now, we will just use this one. In my next session, we will go into the details of what exactly the sigmoid activation function is. And if we have these weights W11, W12, W21, W22, all these are the values of the weights, then for the neuron 1 in the hidden layer, we do the calculations for Z1. You all can do it. And in neuron 2 also, this is the weighted sum of the inputs. First, we have done Z1, which is the weighted sum of the inputs, and then A1 has taken the output value of the weighted sum and then passed through the sigmoid activation function, and we have got some value here. Similarly, Z2 is for the neuron 2, and it is the weighted sum of the inputs, and then it has gone through the activation function, which is once again the sigmoid, and this is the value. And the output neurons calculations also are shown here. So, this is a numerical example which I wanted to show, so that you can relate it to the actual numbers that usually come in real life problem solving. Now, coming back to how to reduce the loss. So, as I was telling, we have the input layer, hidden layer, output layer, and your output or the loss at the output is a function of your target value and A3, which is your output in the or the model's output. Now, what happens is, if we see, this loss is a function of your output A3. Now, if we see here, A3 is a function of Z3, and Z3, while calculating the Z3, all my weights have come into picture, W1k, W2k, they are a part in the calculation of Z3. Also, In Z3 calculation, we have taken A1, A2 also, multiplied them with the weights, and if we go backward, we see this A1 is once again dependent on Z1, which is nothing but the weighted sum of the inputs in the first neuron of the hidden layer. And if we see, this Z1 also depends on the weights. So, W11, W12, W11, W21. Similarly, here also, if we go back here, because your Z3, in Z3 calculation, we have this A2 term also, and A2 is dependent on your Z2. Z2 is dependent on the weights associated with the neurons, input neurons. What we see here is the loss is actually dependent or is a function of all the weights associated in all the edges. So, in order to reduce the loss, the gradient of the loss or the error is propagated, and the gradient is taken with respect to the weights, and it is propagated in the backward direction. And for time being, what we will understand here is there is an algorithm which is called as the backpropagation or backward propagation algorithm, in which the derivative of the loss with respect to the weights are taken in the backward direction, and by this process the weights are updated and we reach a position where the loss is minimized. Okay. We will go into the backpropagation or backward propagation in much more details in my subsequent sessions. So, for right time being, it is the backpropagation which updates the weights and helps to reduce or minimize the loss in the output. So, this is about feed-forward neural networks with the forward information carrying and backpropagation of backpropagation algorithm working in the backward direction to reduce the loss. Then we come to something called as the shallow neural network and deep neural network. We are all speaking about neural networks. Now there is two terms, shallow and deep neural network. We'll try to see what are these two. So if we see, I have two pictures. The first one is a shallow neural network where there is one hidden layer of neurons, whereas in the deep neural network there are multiple hidden layers. Now it is from the picture itself we can say that this network is very, very deep because it has multiple hidden layers, 3 or more usually, and we will just have a quick look into what is the difference in these two models in terms of handling problem complexity, or what are the different applications and feature learning, the things, feature learning in an algorithm. So, we will just see in shallow neural network we have one hidden layer, here it is 3 or more. Complexity wise, shallow neural networks can handle simple and linearly separable problems, whereas deep neural network can excellently handle complex nonlinear patterns. In applications, coming to applications, shallow neural network can be used in linear regression, simple binary classification. Okay. So, very simple tasks, whereas deep neural networks are used for image recognition, speech recognition, natural language processing, complex predictive analysis, this kind of applications. And as we know and as we are seeing that shallow neural network is having less number of hidden layers, so it has a limited capability of feature learning, whereas deep neural networks are capable of learning very complex features. So, usually whenever there is very complex work, we use deep neural networks, whereas where there is a simple work which do not require deep learning or deep neural networks, we prefer going into shallow neural networks because that reduces the time complexity and other requirements in terms of memory and processors and other things, and if it can be solved in a simple way, we go in the shallow neural network. Now, we'll just have a quick look into feature extraction using shallow and deep neural network for a classification problem. Suppose we have a dog's image or a puppy's image and a cat's image, and I want to do a classification, that means telling a dog as a dog and a cat as not a dog. So, what we will do is, in a shallow neural network, the image data is fed and there is a separate feature extractor which extracts the features, handcrafted features for a dog's image, from a dog's image. So, this feature extractor is basically another one single hidden layer neural networks which takes out or does the feature engineering, takes out or extract the features of a dog, and then that is fed to the neural network and classification happens in the neural network, and we get an output Y, that means whether it is an image of a dog or not a dog. Okay. So, that happens in shallow neural network, whereas in deep neural network does the feature extraction as well as the classification together. So, we do not require a separate feature extractor in case of deep neural network, because it can learn the complex features that are present in the image and then it gives the output Y. So, I think that is all for today's session. We will now have a quick summary of what all we have done or what all we have learned today. So, we started with the multi-layer perceptrons, introduction to it, how it looks, input layer, hidden layers, output layers, how they are connected, and then we have seen what is the difference between the single layer perceptron and multi-layer perceptron, and for which kind of applications they are good. Then we have come to the feed-forward neural network, where we have understood what exactly happens inside the hidden layers neurons, the weighted sum of the inputs and the activation functions, and what is the importance of the weights there, and how the output is calculated in the feed-forward neural network. And we have seen these things in details, and also we have seen there is a loss or the error term that comes out at the output layer, and there is an algorithm called as backpropagation. We have just touched upon, but understood what exactly backpropagation does in terms of weight updation. Basically, it updates the weights. Updation of the weights happen after the backpropagation algorithm, and where we take the gradient of the loss with respect to the weights, because weights are the deciding factor for this error. So, after that one, we came to a numerical on feed-forward neural network, and we saw if the inputs are some numbers and we give a particular activation function like a sigmoid activation function, how my outputs are calculated. And then we have come to the deep neural network, come to a shallow and deep neural networks, and we have seen how they are different, what are the applications where we can use shallow and deep neural networks, and how the approaches differ when it comes to an image classification problem. So, that is in nutshell for today's lecture. I hope you have found it informative, and in the next session we will explore in detail the activation and the loss functions, and because they are an integral part of the multi-layer perceptrons. As you have seen, we have used, but we have not gone into the details in this session. We will do it in the next session, which is on activation functions and loss functions. Till that time, happy learning. Thank you.